Good morning. I'm Camila Fernandez, and I will present you my internship work. The name of the project is Time to Event Analysis, and it was a work we did with Calvin, Pierre Gaillard from INRIA, and Alonso Silva from Safran Tech. So the first thing I will present is what is a predictive, or what is the idea of predictive modeling. So, okay, no. So basically, the main idea is that we have a data set and we want to use statistical tools to transform this data set in an executable model, which will be able to make predictions. And an example of that is this data set, which is about house pricing. So we first divide the data set into training set and test set, and we are going to have different features and the target, which will be the price of the house. And so the idea is that we train a model using these features and this target, and then we take new samples from the test set, and we want to guess which is going to be the target for those ones. So in this schema, we can see that more clearly. So we first we have a training set, and we feed a model using this training set, such as so we can get an algorithm which is able to make predictions. So then we use the validation set to we give the validation set to the prediction algorithm, and we have our final prediction. So the idea of time to event is that we want to predict the time until certain critical events occur. And that was first raised by medical researchers. They wanted to predict the lifetime of population. And so, and a very important concept about time to event analysis is right censoring. So what is right censoring? So I have this example. If we want to estimate the death time of people who were born during 1990, most of them will be alive because 1990 was not too much time ago. And so if we only consider the people who are dead, we wouldn't have enough data to make a good prediction. So the idea of right censoring is that we are going to consider both people who are still alive and people who are dead. And so the event of interest only will occur for a subset of the observation. And this time, for the people who are still alive, we will call it sensor time, which it will be a lower bound for the event time. So I have some examples. For example, when we want to predict the customer churn of an enterprise, we can consider both clients who has churn and client who hasn't churn. Also for health, if we want to predict when a patient with certain disease will die, or if the recurrence of a disease, we can consider both people who have died and people who haven't died. Also predicting recidivance, which is when someone goes to prison, and then what is the probability to come back to prison, or what is the time that this person will come back to prison again. Also, we can predict when a couple will break up. And also, if we have, for example, a ruler which is not long enough to measure all the things we want to, so we can do some estimation using some like well measuring and some estimated measuring. And the last one, which is a very important application, is predictive maintenance, when the idea is that we want to predict when a machine will fail, so we can schedule the maintaining of the machines properly. And so I will show you. So we implement many models for 3 different data sets, and I will show you the cable telco churn dataset this time. So here the idea is we want to predict if a client will churn from a telecom telecommunication company. So we have some features such as the gender of the person, if he has a partner or not, dependents or not, and what kind of services he gets from the company and that kind of stuff. And so we separate the data set into training and test. And also we are going to have, so our target will be predict when the person will churn. So we have this column which is called tenure. The tenure is the quantity of months that a person stay in the company, and this one the churn column will be false if the client hasn't churned yet, and will be true if it's already leave the company. So we're going to, if we consider T to be the time of churn, if the churn is false, then T will be at least it will be bigger than the tenure time. So we want to predict the tenure for the test set. And so in this data set, we have 5,282 training samples. We basically divided into 25% for validation set and 75% for training set. And also for the right sensor samples, 73% of the data set were sensor, which means that 73% of the samples hasn't churned yet. So this is an important number of sensor data. And so how we implement these models. So the idea is that we have the training set, we train the model, then we use the validation features to predict the survival probability function. And with this, then we can get the predicted, we can get a prediction using this survival probability function. And we use the validation target to evaluate how good were our predictions. And so for this evaluation, we can use some scores I will show you later. So there are two things that were important in when we train the models. The first one is cross-validation. Cross-validation, the idea is that we take the training set and we split the training set in many subsets, and we each one of these subsets, we split it again into train set and test set, and we train the model for this train set, and we get the score with the test set, with this small test set, and then we do that for every subset of the training set, and we choose the parameters that maximize the score. And the second thing we implement were bootstrapping. So the idea is that we have the validation set, and we made many samples of the validation set, which means that it's kind of a copy of the validation set, but not exactly the same one, but with the same size. And we compute the score of the model for each one of the samples of the validation set, and then we finally consider the final score as the mean of all the other scores. So what are the models we implemented? We did 7 models, but we also tried some others, but they didn't work. So I will only show you these ones. So here we have some parametric models and some other machine learning models. I'm not going to explain how works each one of these, but something which is important to mention is that we implemented this randomized search for almost all of them. And the idea of this is that we, when you do cross-validation, you have to choose which are the parameters that you're going to try. And you can do it by the standard way to do it is using a grid search, which is basically try all the possible parameters. So what we do, we have like a distribution function, for example, uniform between 0 and 100. And so we take a sample of this interval, and we take some samples of this interval, and then we try with those parameters for the cross validation. So it's that's a little is less costable for the computation of the models. So how we compare the models? We did two different comparisons. The first one was with the concordance index. Concordance index basically tells you if for example, this R, it means that the risk of die of the sample I. So if the risk of die of sample I is smaller than the risk of die of sample J, so the time of sample I must be bigger than the time of sample J. So it basically tells you if the risk or the probability prediction is according to the survival times. So the best concordance index we can get is 1, and the worst one is 0.5, which means like it's randomly ordered. And so we think that this index is not as good as we would like to, because it's only compare the order of the data, but we can have like very bad predictions, but if they are well ordered, so it's going to have a good concordance index. So we also implemented this IPEC score, which is an estimator of the mean square error of the estimator of the survival probability function. So this S will be the survival probability function estimated in time t of the sample I. So the idea is that we want to measure how far is the probability function to depending, for example, if I'm evaluating in t and t is smaller than the survival time, so we will want that at that point the person will be still alive. So we will want that the survival probability is 1, and if the time we are evaluating is bigger than the survival time, so we will expect that the person at this time will be dead, and so we would like the probability function to be 0. So, and this is weighted by a function that can be which is this one, and I'm not going to explain it because it's too long. So then the results, I first have the concordance index comparison. So here we can see in the left side, we have the models, and in the x-axis, we have the concordance index. So the red ones will be the ones with randomized search, and the blue ones were the one with no randomized search. And we get that this for telecom churn dataset, Cox proportional hazard model was the best one. And then it was Weibull AFT, and then gradient boosting. So then we have the IPEC score comparison. So something which is interesting is here that we have almost the same order of the models. But I think this score is better because you can also recognize better if, for example, like we can see that DeepSurf has accuracy of 0.12, in this and random survival forest with adaptative nearest neighbor has 0.14. So we can see that this one is almost 2 times this one. So it's more easy to identify how better are one model to comparing to another one. And yeah, so and for IPEC score, I think I didn't say that, but it's better if it's smaller. So in this case, we have Cox is the best one also. And so the other interesting thing that we can implement is feature importances, where we use a function from scikit-learn, which is permutation importance. So we can check which of the features of the dataset are more important for the fitting of the model. So, I mean, for the predictions of the model. So I have the graph of for Cox model because it was the best one for this dataset, and we can see that the contract is the most important feature in the predictions. So we can also study each feature separately. Like for here we have the probability function of the of die according to the the probability function according to the type of contract. So we are going to have 3 types of contract: month to month, 1 year, and 2 years. And we can recognize that the people who has month to month contract has less probability to stay in the company than people who has 2 years contract, which are more stable to stay in the contract in the company. So also we are able to do a comparison of how good our predictions are, and also we can study different we can study how the features in how the features affect our models. And the last thing I will show you is that we were also working on ensemble methods. So we basically, the idea is that we implement a function which is which can get the survival time, and then we average the survival time between one model and the other, and we check using the techniques I said before to estimate the accuracy of the ensemble methods. So in this case, we didn't have very good results because basically all of these models has the same accuracy. So we didn't increment the accuracy of the models by combining them. But for the other 2 data sets I work on with, which were from health, it was we had better accuracy for this. So that's why it's important to mention. And that's the end of my presentation. So I hope you enjoy. Thank you.